friends. You know Dr. Bhujanga as DG DRDO, as a person who was carrying out various responsibilities. I'm not getting into that. Actually, when I was there in DRDO as chairman RAC, I visited his lab. He taught me what are the, how to kill a ship or a submarine. He was making torpedoes. He himself, and if you have to really ask someone that how to move very fast in water, he'll be able to tell you that you can achieve velocities like 100 kilometers an hour in water. So he has a lot of expertise. But what really attracted my attention, once he asked me, please come, have a look at engineering aspects of cochlear implant. Frankly speaking, I didn't know what the cochlear implant was. So that made me learn. In fact, being a control engineer, I used to think that eye is the most complicated organ in the human body. Because I learned somewhere in Miami that eye has got a 13th order control system. Normally we talk of second order control system, PID and all that. But after his explaining to me, I learned that ear is much more complicated than eye. Actually, ear is the most complicated organ in the human body. Now, I have seen him almost a decade of continuous, relentless effort in developing that cochlear implant. When he's nearing ready, so his interest further went to eye implant, bionic eye. Actually, what it is basically connecting a normal color camera to the brain. How he does it, I don't know. So that we'll listen to him. An engineer who has a multidisciplinary aspect in his blood and a very fine human being, Dr. Bhujanga.
Good evening, ladies and gentlemen. And first of all, I would like to thank Dr. P.S. Goyal for his kind introduction. And he was my former colleague and also my friend and philosopher. I'm extremely happy he could spare time and come over here today. And I'm also thankful to all of you for coming for this lecture. It really gives me a lot of pleasure to speak on this particular topic. Okay, this is the topic, bionic ear and bionic eye technologies, progress against hearing disability and visual impairment. Yeah. This is what I'm going to cover, basically introduction, something I will talk about bionic ear and its present status, bionic eye and its present status, then cochlear implant design in which we are all involved, then what kind of business model and humanitarian issues right now with this cochlear implant and bionic eye. Then I will follow it up with conclusions, and thereafter we have a national anthem by deaf children. Right. Deaf can hear, blind can see. That is my statement. Here when I say deaf, deaf means those people for whom hearing aid is of no avail at all. Hearing aid will not help them. They're so deaf. Even if there is some bomb is exploded next to them, they can't hear. They're really deaf. Since they are deaf, they are also dumb because they don't know, they can't hear to reply what back. That's why they are dumb. They have the faculty to speak, but they cannot speak. That's why they are deaf and dumb. We call them profoundly deaf. Doctors call them sensory neural deaf. So similarly, blind. Blind also not with some support, some lenses and some, we can make them see, some people. But I am talking about blind who are profoundly blind. That means the retina, which is the basic sensor of vision, is completely damaged. So in case of deaf people, retina to the eye is cochlear to the ear. If retina is lost, we are blind. Cochlea is lost, there is a damage, then we are deaf. So I am going to talk about this cochlea and retina, how to with the latest technologies available, can we make today, what is the status of this bionic ear and bionic eye? So basically, bionic ear is a neural prosthesis designed to give the gift of hearing by electrically stimulating nerve cells inside the cochlea. I will go into more details now. Similarly, bionic is also retinal prosthesis, replacing the retina to produce electrical stimulation of photoreceptive cells in the retina to instate a sense of vision in the people who are profoundly blind. Basically, what we are doing is, we are short-circuiting cochlea or we are short-circuiting retina, respectively, in case of ear and eye. So that is how to short-circuit the system. Let us just look at this normal ear, which you all know. So this is the normal ear, and we have, this is how the sound propagates. Then it reaches what is called tympanic membrane. That is the first. So this part of the ear is called external ear. So when sound falls on the tympanic membrane, the membrane vibrates. So then immediately the vibration is carried by 3 bones. They are called ossicles. The different names, last one is called stapes. So these 3 bones, the sound energy from the tympana is carried by these 3 bones to the cochlea as vibrations, as a structural vibrations. These 3 bones are the tiniest bones in our body. We have 212 bones in our body. These are the smallest, and the stapes, which is in the shape of an anvil, which really vibrates the cochlea, is as small as fraction of a gram. If it is lost, we are completely, that part of the ear, middle ear will not work. Any of these 3 bones. So some people have problems with the bones. So they have an accelerometer to pick the vibration from the tympanic membrane, then an actuator to excite the cochlea. So that is how the bridge is done, and that is a hearing aid. Similarly, tympanic membrane is a problem, there is a hearing aid which can help. But if it goes to next after the bone, the small bones, ossicles, what we call is a cochlea. This is the cochlea. This is the shape of a small snail-shaped body. It is a snail-shaped body. I will come into the more details. Apart from that, I would like to show you 3 more small canals here, semicircular canals. These are the 3, 1, 2, 3. So they are very, very important canals. This equilibrium of the brain, we don't get checker. All that is controlled by these 3. These 3, they manage the navigation, everything. So ear has got not only giving the gift of hearing, sensation to sound, but also the equilibrium of the person. When he is walking or running, when he goes round and round, he will get this thing. But some people get vertigo. If there is a defective part in that, you get a vertigo. So this is very important body. It's also part of cochlea, in fact. All are going through cochlea to the brain. So just little bit about cochlea. What is a cochlea? Cochlea, as I showed you, this is in the form of a snail shape, right? Now if we can stretch it, that is the bottom picture which I have shown, it will be like this. So if you see that cochlea, the tube, which is as lengthy as about 3 centimeters maximum, not more than that. So 2.5 to 3. So this is made into 2 partitions. One partition is called basilar membrane. That is the name given to that. Another part is one having the hair cells touching the basilar membrane. So when from the previous figure, if you see from the ossicles, ossicles vibrates and goes into the cochlea. That means it is the vibrations. The cochlea is filled with fluid. So from that point onwards, it becomes a fluid vibration, fluid-induced vibration. Fluid also vibrates, right? So in this cochlea, what happened, which when we stretch it, the basilar membrane, fall below which there are the hair cells, which are fixed to another structure. These hair cells are basically, they respond to electrical signals. So that means basilar membrane vibrates, that is picked up by these cells, convert into electric field. That means like piezoelectric effect happens there. But not exactly piezoelectric effect, because there is no such material there. Happens, that means the hair cell bends, it releases an electric signal, electric potential. That's how it happens. So when you vibrate, the hair cells are bent in a particular fashion, electrical signal is created that goes to the brain through what is called audio cortex. That is how brain senses it as a sound, right? Now this basilar membrane also got, the hair cells are in 4 rows below the basilar membrane, and it is like the violin. Violin also has got 4 strings. And it exactly, if you see the basilar membrane, it's a very beautiful system. You can call it a spectrum analyzer, or you can call it a violin, or you can call it a veena. Because within the small length, all your frequencies are fixed. At one point, if you touch it, basilar membrane, it gives 100 Hz. At another 1/3 octave distance, if you touch, it gives 230. Like that, you keep on giving within this 3 centimeters length. It can excite as low as 20 Hz for a healthy human being, as high as 20 kHz to a healthy human being. That is our sensation frequency wise. Though we will not have with age, it gets changed. So this is very important part of that. This is how the signal is now transferred to the brain. Now, how does the bionic ear? In a very simple way, I have put it here. This is the sound is picked up. Yeah. See, sound is picked up from a microphone. Somewhere a microphone is there. It is received. Then it goes into a body-worn processor where the sound is divided into filter it, whatever frequency you want to select it. Say, in the one which we are doing at DRDO is from 200 Hz to 8 kHz in 8 filters, and all that is again converted into digital signal. Then all the digital signal are converted to serialize it, because we can't transfer data because the electrode is the cochlear implant is inside. I will come to that. So to transfer it, we have to serialize it, then encode it, then pass through into the skin, and then it picks up inside, and it then again it is parallelized and pressed, given to the 8 electrodes which are for this purpose planned. These 8 electrodes will excite 8 places in the basilar membrane. That's what exactly going to happen in this. So this is the basic design behind with which it is made. What we call generally the inner portion, which is implanted, that is called receiver and stimulator. Receiver, stimulator, we call it. The external portion is called body-worn processor, right? Now, external ear is here, tympanic membrane is there, bones are there, then cochlea are there. Now, we will not pass this electrode through normal ear canal. We don't pass through normal ear. What we do is behind the ear, we make a strip, we open it, make a hole, and put the electrode through that, and then slowly insert it, and it will go into the cochlea. So this is the electrode part you can see. These are very tiny electrodes are there. In this case, about 20 electrodes. Some are dummy to give the stiffness. Some are actually activating active electrodes, and they're all microscopic. We have to see in a lens. They're so small. They're so tiny because the diameter of the cochlea is also very, very small. So when you insert it, it should go and sit nicely. So if you have more stiffness, it will pierce and go out in some other portion. If it is too soft, it will kink back and come back. So designing it to meet that particular specification is extremely difficult. If you make some hundreds of trials, then we get one particular combination where we have to fix it. That is how the electrode is designed. It is quite a complex part of it. And even the electrodes doing welding with so many wires, because each electrode has to carry one wire, then is a return path, negative, all wires will come. They are all in micron size wires. You have to literally see them in the microscope and do the welding also at the microscope. So that's why it's a very complex system, and it is not easy to realize. Even some of the latest companies also having problems with the electrodes. Still, they are not able to 100% solve it. So this is how the electrode is finally inserted into the body and nicely pushed into the cochlea. If you see basically, you can say a zoomed version of this, how this is entering into the cochlea. You can see that. Then when a doctor operates it, what he does is he opens behind this ear and opens up, then he make a bed for it, because the size of the implant, which is not only electrode, is also having electronics. There is a chip there. So all that put together, it is some shape and some size and weight. All are within the limits of acceptable size for a baby of 2 years or less. It should go. And when the baby grows to 80 years, 70 years, we will not going to change it. It is designed for life. So the electrode length extra we keep it. As the head grows, the electrode length will be automatically pulled by the cochlea and it will be staying there. That is how it is designed. There are now people having as old as 30 years old cochlear implants in their human body and working this one. So this is how these operations, generally surgeons are specialized. Not all ENT doctors can do this. They are highly trained. We have about in our country best doctors, about 20-25 of this kind, who are having sufficient experience, who can undertake this. Even in US, I was studying some reports, there are not more than 100 doctors who can do this. Though they claim 200, 250 doctors are there in US, but really experts, top experts are about 100. It is about 3 hours operation and it is done. And it is. Now what is the status today is we have 25 millions in the world suffering from profound deafness. And in India, we have about 1 million deaf people who need this implant. If you go to a deaf school, you can see how many children are there. We really feel for them when you see them. They're profoundly deaf, they're mute. And 1 in every 1,000 children are born profoundly deaf. Every 1,000 children that are born, 1 is deaf, or profoundly deaf. And in every, today, out of 100 children, we are able to implant 1 child. Remaining 99 are returned back saying that they cannot afford it. This cost is so high, they cannot afford it. So that is today the problem. Nearly 0.5 million people have been implanted, so far 50 lakhs people, maybe more. The figure when I took it, it is almost 6 or 8 months back figure, must be more now. That many have been implanted also. So this, actually you can see there is a lot of analogy we can make between bionic ear and bionic eye. I will just very briefly talk about bionic eye. There are 2 types, one is epiretinal and one subretinal. We will just talk about epiretinal. In this case, just like we have a microphone to pick up sound, we have a camera to pick up light here. Then that is instead of going into the body worn processor there, this is going to another processor, we can call it wireless processor, which is also outside the body. Once that is done, the data is digitized. It is all in a pixel shape, and this then transmitted to inside. That means inside the eye, I have to keep a chip to receive the signals. Now that chip, again, like in case of bionic ear, we are sequencing from sequence serial to parallel. Here also do it and apply in an electrode which is in the shape of in a retina. You know the size of retina? Retina size is 4 mm by 4 mm. Actively we can use 3 mm by 3 mm. We can't use more than that. In this 3 mm by 3 mm, we have to make at least 64 electrodes. They have achieved 64. Now I think people are planning 600 and all that I'm hearing from this same advanced bionic, this Australian bionics who are making this bionic ear. They are also now doing bionic eye. But they are not the number one. Number one, I'm going to explain who is that person who has done that. So, actually in nature, retina is nothing but having about 10,000 sensitive photo detectors, you can call it, photosensitive detectors. When light fall on this, I think somewhere I missed it. Yeah, this is the eye, right? When light falls on this retina here, okay, then that is automatically converted into the electric signals and goes to the what is called optic nerve or visual cortex, goes to the brain visual cortex. There are 2 visual cortexes behind us here, one for the left eye, one for the right eye, and like we have 2 audio cortex also. So both are almost similar ones are there. So what we are going to do here is, in this case, after body worn processor picks up the digital signals, it gets slowly transmitted to inside. Inside there is a system like receiver stimulator. In the case of bionic ear, we have bionic eye also. Then that handles the data. that gives all that 64 array, 8 by 8 array is there, which is there. So it gives signals in a pixel form, and that is recognized by the signal goes to the brain through optical nerve, then it is recognized the brain as vision. Okay. So here also exactly same. If you can see the principles are same, whether it is a bionic ear or bionic eye. But we have made in the world a lot of progress in the bionic eye, but we have not made as much progress as we have done. But it is being now, people are making a lot of effort and trying to do that. Okay. There is also called subretinal prosthesis. This is a simple concept, concept-wise. Retina is nothing but photosensitive area. Why can't we replace the retina with some material having the same properties? So people have tried that. Subretinally, that means inserting, not the previous one, epiretinal was behind the eye, whereas this is in between. We can flush it inside a chip. But they found that natural light gives 1,000 times less. Whatever material you put it, best material available in the world. People have tried photo detectors, whatever available material, they are able to get signals 1,000 times less. That means the natural material is 1,000 times more efficient. That is the reason they are not able to make any headway on that. There are some persons working in Bangalore, in the JC and Narayan on this. Is trying to see any other new material and all that. Okay. Hope we will be successful. If that is, then it's the simplest. You just replace the retina with a small another synthetic photosensitive material. But we are far from that. We are nowhere near today. That is why that is not working. People have tried it, but it's not working. If you see the research, almost 1950 onwards people are working in the case of bionic eye. Whereas in case of bionic ear, it is only in 1960s it started. Before that, of course, people have realized various, even Volta's battery, he has discovered there is something with the ear, brain is recognizing only electrical signals, not sound. So some theories he has made even those days, 200 years back. So moving on, subretinal prosthesis, which is used as a bionic eye, was not of any help because it is about 1,000 times less sensitive than the natural material that is available. When it comes to status, we have nearly 45 million in the world who are profoundly blind. And India, we have about 1.4 million, children, out of that is 1.4 million children. In India, we have about 15 million profoundly blind people, largest in the world. It is a very dubious distinction, actually. Largest in the world. There are many reasons for it, because of lowest state of society and lot of diabetic, even we are becoming diabetic, diabetes also, we are already largest diabetic people in this world. So those who are having diabetes, they are also leading to blindness at some stage of this thing. So that's how this is a very pathetic situation when it comes to India. We have 80 million diabetes people. So the vast majority of childhood blindness happens before age 5, a period when 70% of learning is through sight. See, a child, if he gets all this experience, life, knowledge, information, everything before 5 years, that almost 75% of information he gets into the brain through eyes below 5 years. You imagine if he is deprived of natural eyes, what could be the problem for him? So this is the status of eye problems, blindness problems. Now, cost of implants. The cochlear implant today costs in India, well, let us talk about India only, about 7 lakhs with including operation charges, everything. Otherwise, it costs about 5.5 to 6 lakhs today. Bionic eye, I think, is just out of question. I have seen latest thing is about 50 lakhs. It is written as without estimate. And there are no doctors in India who can implant a bionic eye as on today. Right? Send him to US and do that. And even total operations done so far is about 50, not more. That is what is the bionic eye. So this the cost is really unaffordable. This is the reason why we are not able to make any progress against these two disabilities and impairment of. So we have to think, if we are to make a progress, what should be done? Another thing is, in case of bionic ear, we have to implant a child before the age of 5 to 6 years. This is very, very important. If he is implanted after 5 years, what happens if he is deaf from the birth? See, it happens from the birth. because of certain diseases or the unhealthy atmosphere in which the child is born, for various reasons he gets it, then or genetically also. So if we don't do it in 2 to 5 years, there is, as I said, there is audio cortex, there is a visual cortex. So the audio cortex portion, since the brain is working that portion, brain is active, but brain is not getting signals because cochlear nobody to shorten the short circuit the cochlea and give the signal. So what happened automatically, natural process, video cortex will take over the audio cortex and he can listen better. He can see better, not listen. In case of a deaf person, he can see better, but he can't listen at all, mute. So it is a compulsory, we should do operation before 2 years. Now today people can do in 10 months. There are doctors doing 10 months. It's just a small child, right? So people are doing, and that child is almost as normal as a normal human being. If you can implant before 2 years, he will grow as though he is very normal. So this is one. In case of bionic eye, of course, children is not necessary. Most of the problems are coming in late 20s, 18s. Maximum percentage of problems. Retinitis pigmentosa is the worst disease which is causing this problem in case of blind people. So for them, of course, any time. But in their case also it happens. If blind person is not implanted, then his blind visual cortex is taken by audio cortex, and he can have somewhat echolocation, that capability. That's why blind people can see by like bats, echolocation, though they do not have ears. So that capability they get because that portion of the brain is taken over to take care of the audio part of it. This is what we have done some work. What is the right specification for it? So one of the specification, I would just quickly go through that. It should be low cost and affordable. We should make one for India. Then how many electrodes we can go into it? There are, again, commercially people are exploiting. Somebody says 20, somebody says 22, and he claims mine is better. It is not really nothing to do with that. So experiments have been done by a large number of people. They have found we need only 4 electrodes, minimum. 4, 5, 6, everything is same now. If you, between 4 and 8, the difference is 90 to 95. That's all. If somebody put 24 electrodes, only commercial exploitation of the thing. Every time they're increasing it. Unfortunately, if you see the technology in the last 20 years, there is no growth of this technology in case of bionic ear. It's only commercializing some changes in color, put this and increase the cost and having that kind of thing. Another thing, what we have done is, since I talked to I will come to that who was a guide for us. So when I discussed with him, 8 is enough. So what we have done, we have put 12 electrodes. Any 8 we can select. Okay, that is how it is designed. Then we have gone through what is called CIS strategy. Continuous interleaved sampling, I will come to that slowly, okay? And you know, if I have 8 electrodes, each electrode I have to excite the brain at least 1000 pulses per electrode per second. Each electrode has to, that means 8 into 10,000, 80,000 pulses per second I have to excite the brain. At that rate only brain can recognize. If I excite at 550, 400, 300, brain cannot respond. That is one of the conditions. So it is the limit is about 750 or something, below which it can't respond, above which it responds. So we have selected 1000 pulses per second. It's a big, huge difficulty in selecting these things because the electronic size and chip, everything is involved. So it poses a lot of challenges. Then what we call biphasic pulses are there. Because if you have only single phase, it may heat up the tissue. So biphasic means one heats, the next one will cools, mean equilibrium maintains. So that is because we are keep on exciting with these pulses, no? So we don't want charring inside happen. So that's why it is done. Then transcutaneous with RF link. See, inside there is no battery. There is no place to keep battery, and it is not possible to keep battery. Like if there is a small leak, it may explode. So you can't have any battery. So it has to be, so the signal as well as the power are to be transmitted inside. That means you have to design some RF system where there is inside one RF coil, outside a RF coil, antennas. And the thickness is the skin thickness. So within a skin thickness is not more than maximum 5 to 8, 6 mm, we have designed for 10 mm. So because if there is a slight bending or something happens, so or some skin thickness varies with the age or something, so to take care of that, it is designed like that. So that is called transcutaneous link. If we can make a hole and pass through the brain, the body, it is called subcutaneous link. Original first time when Grammy, the Australian doctor who invented this, he has put a big box on the head and made a hole and put the electrode inside. And it was, the patients were moving like that for their life. The original model, if you see that. Later on, with the IC chips coming, everything come, they're able to put one inside and transmit transcutaneously. So at least the infection part. Otherwise, there is a protruding outside connector. If somebody pulls it, it is dangerous. It is made such a way that it can't be pulled, but still, there was a thing. Because I have met one such patient in US. Then monopolar, these are all how to excite. See, there is a various ways. Like a battery, we have positive, negative, bipolar, monopolar. Then impedance telemetry. That is very important because I want to know the status of the electrodes. After when I put it by mistake, the electrodes are so tiny in size and weight and thing, it might have damaged. With the forceps, if you try it also, it may damage. So to avoid the damage, I must know the status of the electrode at any point of time. So I have a telemetry system. I know whether it is opened or shorted or active or how much ohmic value it is there. That is also important. All those things we should get, otherwise doctors won't accept such a without that. Then body worn processor, that there are now two types. Body worn processor as size as our this one mobile, and now the latest is even that mobile is converted into a small chip and behind the ear it is kept. It is called BTE, behind the ear. That is a small. In our case, we have not gone to that stage because let us prove this, then we can convert it. It's a conversion not going to be difficult. Inner one chip we cannot avoid, so we have made that also. Right? And of course, all materials have to be completely biocompatible. We are using platinum, iridium, we are using titanium, we are using elastic rubber, varieties of materials are used inside. It's not only materials, the process you did, what kind of welding you have done. You have used somewhere laser welding, sometimes resistance welding, all these things you have done. So those processes should be tested on Indian human being and certified. Otherwise it will not be accepted for implantation. So this is the system, very quick look, you can have it. This is the body worn processor, this is the implant, this is the chip that is inside, one of the DRDO labs has made it, and this is the electrode, there is a return path, earth, and this is the coil, and there is a magnet inside here. This magnet is important because inside coil, outside coil are to be aligned. If they don't align, there is a loss of power. So we have to align it further to use the magnet to keep it in always intact. And this is how it is implanted. The skin is removed and this is put in that place and covered it. So this also needs a lot of software. See, because audiologists, when it is implanted, we have to see that the levels, intensity, the amplitude, frequency are all properly tuned. It should not cause too much of pain or displeasure, and at the same time sometimes it should not become below threshold of hearing. So it adjusts it. So made a lot of software is done, and it is done by audiologists. They do it. Keep the patient after implantation. After 4 weeks, they activate it. Up to 4 weeks, they don't activate because there is a healing of the wound and all that. Once it happens, then they activate it. Once they activate, then they go into what is the minimum position. Slowly they increase. Once he gets sudden thing, he will not able to tolerate it. So suddenly, very slow they increase. Each frequency band, they have to keep trying, take his response, wait, take his response. It is like a child. When a child, 10 months, he start talking in a very funny words and all that. Only after about 1 year or so, he gets clear sentences. So that process is not because the brain is developing. So same thing here also. After implantation, it starts happening. That's why audiologist has to see at least 6 months to bring the person to train to a normal hearing capability. So that happens. So all that period, this particular type of software is required, and it is done. This is just I would like to say, so many agencies are involved in doing this research in India. NSTL, Debel, I'm happy, Debel director is here, and former director Debel also is here. Andhra University, one very great professor, he worked with me. is working with us. Anurag, who has made the chip. Sitar, who has developed the PCB, which is a very important thing, because inside the chip, not only PCB, there are analog components also. So those components are accommodated, everything. Then some Technoceras company, DPAS, we have done animal trials. Bionic, we have done biocompatibility trials. RCA, we have done ESD, EMI, static, all these things. And Armed Force Medical, they cooperate so well. We have done a lot of cadaver trials. We have to do on cadavers also to give them confidence to the doctors, where this will go and sit properly, what kind of templates they have to use it, and things like that. Pastronics is is a company where we are finally doing the assembly and sterilization and packaging. Because packaging and sterilization also, there are very strict protocols on this particular one. So that is being done. So it's a very, the details are only, I can very quickly go through these details. This is the external coil, this is internal coil, this is the skin. This is skin. So when we are doing it, we are using, inside for testing in the laboratory, there are simulated materials. We call them saline solution, ringer solution. It almost imitates the fluid content of the ear, that kind of thing. Then we have done some animal trials. We have done on cats. There is a big joke on that, because cats are not allowed. We are first allowed to do guinea pigs. We have done some guinea pigs. Then we have done on rats. Then somebody suggests you have to do cats, because cat is somewhat nearest, not nearest to the human, but somewhat nearest. It accepts only 4 electrodes. It doesn't, that's such a small. So cats were not allowed to do these tests. So at right environmental department then they gave, but they gave with a small thing that any imported cat can use, not Indian cat. At least on paper they have said that, though we use Indian cat only, but at least on paper, today that is the kind of condition we have to do these experiments. And body worn speech processor, of course. More and more in details, how we do this digitization, how it is speech coder, many parts are there in this. This is external part. And frequencies, as I said, we have about 8 bands, 200 to 5.5. Now it is extended, in fact, up to 7.5 or so it goes. So that covers the total range. And even somebody wants to speak on telephone wearing this, he can speak, because telephone thing is between 500 to 4 kilohertz, not more than that. So you can comfortably talk on phones, telephone also, and mobile also you can use it. And it will not interfere with the signal. It is designed such a way that frequencies and everything is taken care of. So this is what I call interleaved sampling. This is a wonderful work actually. It was done by one gentleman. I will come to that, so you can remember this. This is called this. All the electrodes are not given same time signal. There is a slight delay between one, maybe order of few milliseconds only. But the delay has been done. I will show who is that person in my future slides. Then this is inside part. Inside, these are all chip. We all made into a chip. All the circuitry has gone into that. It picks up, then serialize it, parallelize it, and all those things. I will not go into these details. If somebody is interested, yes, we can discuss separately. Then impedance telemetry, I was telling you the purpose of impedance telemetry. You must know the status of the electrode any time of the person in his career, in his lifespan. So that can be done. Then various experimental setups we have used to do these tests and all that, waveform analyzer, so many things. This is how, as I said, audiologist using the clinical programming developed by us, he can get all the data, how he can tune each frequency up and down. The doctor can tune, audiologist as well as doctor, they adjust so that the most comfortable level is there for the. Yeah, this is a cadaver trial I was mentioning, which was done at Pune. And it is very difficult to get cadavers also. I was told there are so many bodies we can use it, but to get one cadaver I was taking 6 months, because we need a fresh cadaver. The immediate of death within few hours we should do, otherwise the fluids are getting dried up. Once you dry up, the results are different. And you can't get cadaver within few hours because there is a police department involved, then anatomy department who is supposed to do some, they put that things. then only they give it. They take minimum 24 hours. So we used to wait and we used to pull out and do all these things. Then apart from we have to do all these tests, I think I have mentioned shock and vibration tests, electrode active, hermetic sealing, impact testing, destructive, crush testing, reliability, auxiliary aging, all these tests it has gone through. Right. So coming to Bionic, I will not give some work we have done in India, but I will not give those details, but just I will tell you how the US project, this was the first Bionic eye project done by Humayun, Mark Humayun, okay, and he was lucky to get $100 million funding, and he has spent 25 years for that, and his grandmother became blind. Then he took a decision that I must do something in this area and I must work. He was not able to accept his grandmother suddenly become blind. In fact, I also did this cochlear implant because when I was very young, I had a friend who was deaf and dumb at the age of 7-8 years. We used to play together in a remote village. He was my best friend. So I also used to think those days, something we should do. So he was funded by National Eye Institute, NSF, then Department of Energy. All these put together, they gave him $100 million, which is a good amount, and he has worked 25 years on that, and he has come out first plant Argus 1 with 16 electrodes, then Argus 2, second generation implant with 60 electrodes. This has been now, this FDA has given permission for that to implant in 2015. Coming to Bionic, I just drawn, no, in fact I explained to you, there are a lot of commonalities and more or less it can go together. Many problems like implant coil is there inside. Here also RF is there. Electronic case, hermetically sealed, both sides are there. Electrode array, they are also there. Here it is there. Type of electrode array that differs. We have to design for that. Then pickup, one is camera, one is microphone. One Similarly, required during implantation startup test, the electrode impedance measurement is also there in both cases. So there is a parallel. It's not easy, but one is somewhat easier, one is still more. One is Bionic ear itself is very difficult. This you can say maybe 100 times more difficult to realize it. And we have ophthalmologists, audio. So basically, if you see the totals, I have conceptualized it, then we have undergone design, then we have hardware software realization. After integration, we have gone for animal trials. Then we have biocompatibility trials, then cadaveric trials, then documentation. Then we have gone to DCGI, Drug Control Journal of India, for approval. He has to give the approval, otherwise you can't implant. So he has given the approval. So then now it is at the stage of human clinical trials, and it is being pursued very vigorously by us. Then of course after that production marketing. If you see in the history, we all know the Helen Keller is a very famous lady. She is an activist and author, lecturer. She was both blind and deaf. She was not she was profoundly deaf and profoundly blind from the 19th month of her age. So, but amazing that she lived 85 years full life, and she was a very intelligent person, and she was asked by some reporter, Madam, you want restore blindness or you want to restore deafness? Which one you want? If God wants to give you only one. And everybody thought she will tell eyes, but she said, I want hearing. So reason she said is blindness separates people from things. Deafness separates people from people. Another thing, one can imagine blindness. We can also imagine by closing our eyes and sitting in a very dark room. We can see what is blind. We can't, after one checker round, going around, we can't make out one. But we can't visualize what is deafness, because there is no place on this earth where there is no sound. If you go into an anechoic room where sound is reduced, you start hearing your own body noise in the ear, a heartbeat, all you start listening to yourself. So if you go to a forest, you see the wind, breeze and leaves, So that's why you can't imagine what is really deafness. We can imagine blindness. Maybe that is the reason she has said that. These are the three people who are now, the Grammy Clark is the inventor of this bionic eye ear. In 1960s onwards, he did, after 25 years of research, he produced the first approved implant, FDA. And this gentleman is the one who gave this CA strategy. He is Blake Wilson. All the three got a Med Nobel Prize. So he is the gentleman. When I was in US, I wrote to him that I am interested to develop this. Then immediately arranged a flight, everything for me. And he received me at airport. He took me and we sat for 2 days. Then we prepared the specifications. That's how the specifications have been made. And after about 6 months, he visited India on his own. And he has discussed with me. He said, you are right path, do it. Then he went, met Abdul Kalam, because we wrote letter to him, he was president. Then he left. So what great thing he has done, the CA strategy, he has made a patent, but he gave the patent free of cost to society. Otherwise, you would have made at least $1 billion on that. And that is used by all the four companies in the world. There are 4 companies now in the world who are making it. Austria, Australia, America, and France. France one is not accepted, still FDA approval. China also trying, they were not able to come up, that's what I was told. Korea also tried. And Korean team came to India to discuss with us at some point of time. This lady is the who started this company, Medel in Austria, one of the first companies. Of course, Australia is the number 1. But so she also shared this because she has improved the productivity model and all that. So there are such great people here. This eye is developed by Mark Humayun. He is a Pakistani American. He has won the US highest award for technology achievement. Mark Humayun is to receive the prestigious National Medal of Technology and Innovation from President Obama. He is a testament to American ingenuity, announced Obama. So he has developed this Argus 2, commonly known as the bionic eye. It restores vision to most blind people. Only thing is, so many millions spent, but he is now marketing his product, which is what I said, 50 lakhs and above, and somebody puts it 1 crore also. But he's also Indian, we can call continent, Indian continent. Of course, he has said that if we continue to develop this type of technology and begin to understand the new electrical language of pulses to the brain, to the eye, we can apply it to other parts of the body and we can change our world. I mean, it is DBS, deep brain stimulation, that is also now to some extent. And like that, there are several stimulation things which we can to improve the state of the body. Of course, this is what Humayun said, almost 30-year journey for him to complete this work. So one should really appreciate if somebody supported him all these 30 years. So he said Alfred Mann was a particular help as he started a company based on my idea, which enabled the bionic eye to be commercialized as an Argus 2. So my concern is, why I am talking main is, when a cochlear, see, in the 21st century we are now, the technology available, but still so many people are deaf. So many people are blind. Okay, blind, at least bionic eye is not developed, but bionic ear has developed last 1985 onwards, it is there. So this is the, why should we remain? What can be done? It is such a helpless state. So governments or society, should not they do something for these hearing disabled who are helpless, incompetent and dependent? In the industries, technology makes things better and cheaper. See, mobile phone, it was costing 5,000, now it is 500 rupees. But in case of this bionic ear, they have increased some, now as I said, about 3 lakhs are implemented. But the cost has not come down. When volume increases, cost should come. That also, that benefit is not given by these 3 industries. Now, of course, 4th one. In fact, Moore's law predicts computing cost falls every 2 years or 18 months or 2 years, right? But in case of this healthcare, every 13 years it is doubling. That is the present status. They say something new model has come, the cost is increased, and doctors say this is better than that, you go for this. It may be 1% better, but still the cost is high, and that's how the market is changing. That's why for every 13 years, the cost of healthcare is going up rather than coming down. It should come down at some stage. It's not happening. A study conducted by Johns Hopkins University reveals if you see the cost of the implant and cost of a study conducted by Johns Hopkins reveals that the society can save about, no, what I mean, rehabilitation. The government spends money on rehabilitation. That is more than at least 10 times the cost of the cochlear implant. Instead of having deaf schools, deaf vehicles, these for so many things, instead of that you give one cochlear implant, it is much cheaper for the government. That is to be realized. It is not happening. They are ready to spend on rehabilitation rather than this. So yields cost utility ratio, some calculations have been made. Governments have to seriously think of ways to shift a small percentage of expenditure from rehabilitation to do R&D. See, somebody has developed, the companies will not give. So somebody has to develop. In our country like India, having so many laboratories, so many engineers, so many experts, we can develop it. It's not a big thing. But there is who will bell the cat, or giving funds. This somehow it is missing. There is a very unfortunate thing. People are not realizing it. In fact, I have met several big people, Tatas, everybody. I asked the funds. Everybody said, once you develop it, we will give. So once you develop it, it is different. There are so many people waiting. Once you develop it, to take it. But there is nobody to help us. This is our Indian present status here. Even the other one also, US, some of the foundations, they are spending money for AIDS and cancers, but they are not ready to spend for this. See, they are diseases. This is not disease. This is a disability. He is born like that. He has to live the whole life like that. So they have to spend it. That thinking somehow is not coming. This is an unfortunate thing. So estimated cost services, special education, these are all, it will pay by what I said is repeated probably here, right? So how to make cochlear implant affordable? So a lot of R&D is required. So somebody has to fund some R&D, the cost. Then basic materials cost, production cost, distribution, they all have to be thought about it. Then trial and evaluation, all have to be evaluated thoroughly. Otherwise, there are even today some implants are giving, people are dying for certain either mistake of doctor or implant design or quality control, something is happening. There is a small water vapor inside in the implant, it is leading to meningitis. Immediately the child gets into problem. So these are all costs involved. So India has got large number of R&D centers, what I have mentioned, and we have to make chips, several labs, designers. We have semiconductor in Chandigarh complex. We have many DRDO labs, ESR labs for experts. Institutes like IASC, IITs are there. All, if one is paired and joined together, they can make definitely such implants. It's not really, and government of course has to support it. It should be a national cause rather than an individual trying to do it. So if we have it, we can produce low-cost, affordable device required for the whole world. It's not only, in fact, cochlear implant, India is a developing country. There are countries, low-income group countries, we call them, the total annual income is lesser than the cost of an implant. So how can you think in that country, ever anybody can have an implant? It's impossible. So we have to, I just made this, whatever I said, I put in the form of a conclusion here. We have to build upon a healthcare access model that is open-ended and has positive aspirations with strict policies on adoption, diffusion of new technology. Like I said, Wilson Blake, he has given society his patent. I don't want to ask everybody give like that, but it should be given at some premium cost. Let them have some money for that. They know definitely, because they also done a lot of hard work. Otherwise, it would not have come. In case of this gentleman, this Wilson Blake, he was in a triangular research park in North Carolina, where I went there. So he was having a patient who was having an old model where there is a connector. So what he did is, since there is a connector, he paid that lady, she's an old lady. She was very intelligent. She was knowing music and all that. When he took me, she got scared. I will touch her or something like that head. So then he told, no, his friend, he has come. He will just see your implant part. Then, so he could do research on her. He could put different signals. He played with her. And he used to ask her, how is your music? How are you listening now? With this kind of, because everything can be done in the body-worn processor. So because of that, he got that idea of interleaved sampling. That means don't excite all the electrodes simultaneously, because there is a cross coupling between electrode and you are trying to 100 Hz, the basilar membrane 100 Hz is one point. If you touch next point for some reason, it also may produce again part of 100 Hz. So these two will join together, it become a noise. It kind of this thing. So in order to avoid that, his idea has come. He has done that. Interleaved sampling because of that particular patient who otherwise I can't put inside in a normal human being, I cannot play with somebody's implant, cochlea. But in his case, in this case, it could happen. That's why he did it. So, and he brought out this, that's why he was very ready to give it to the society free. That made, and all have immediately accepted that. Till that time, all cochlear implant people are suffering to make it. So another inspiration is Dr. Kalam. He was always encouraging about this project. Almost 1 month, he gives a ring his office to go and meet him and brief him. He used to be so fascinated by that. Somehow, though he was the president, he couldn't help in terms of funds. He told, I have the total money allotted to me is 50 lakhs. For which, anywhere any letter come from some corner of the country, some child is sick, I am sending 20,000, 30,000 like that. But I don't have plum. So he couldn't help in that respect, but always inquiring and encouraging and things like that. Thank you all. If you have questions, after that I have a national anthem by deaf children.